Welcome to ECE203. This is a lecture on the topic of phototransduction. So if you're following along with the textbook in the Sarpeshkar book, I do recommend reading chapter 11. And then we will rely heavily on a paper published by Carver-Mead and authors entitled Analog VLSI Phototransduction that is very interesting to read and will be discussed heavily in this lecture. So what do we mean when we say phototransduction? Well, the general definition of phototransduction is the process of converting light, which exists in the form of photons, into electrical current that we can measure with some, electronic circuit. Now, obviously, this happens in things like digital cameras, fiber optic receivers, photovoltaic energy harvesting sources, and so on. It also happens in the eye, although technically it's not going into an electrical current, it's going into an ionic current, but I think you get the idea. We do phototransduction in pulse oximeters. If you want to know your blood oxygenation level, for example, they are typically performed optically, immunoassays to analyze biological samples, and so on. So anytime you're using optics, you typically need to perform phototransduction in order to make your optical system work. Another example application is something called a retinal prosthetic. And we have mentioned this application earlier on in this course, but let's just take a slightly larger dive into what we mean by a retinal prosthetic. Well, these are devices that are implanted into the eye and used to restore vision to patients who have some sort of degeneration of their retinal cells. In other words, they're blind or very hard of seeing. And the way that this works is you have some sort of camera system. Now, this could be placed on the surface of the eyeball, it could be placed on glasses, it could be placed all the way in the back of the eye. We capture light information across many pixels. We represent this light information across these many pixels as some sort of electrical signature that we then go and stimulate the retinal tissue that is nominally degenerated in order to try and create the action potentials that will get sent along the optic nerve to the brain to let the patient, experience the sensation of vision. So this sort of application involves a biological system whose phototransduction functionality has been damaged somehow, and we are trying to recreate it artificially. Building a retinal prosthetic is extremely difficult. In fact, there's a startup company in San Diego that is trying to do this, and actually they're making very good progress. But it's very difficult. There is one commercial company that has done it. Unfortunately, they went bankrupt. For many reasons. One was that their technology wasn't that great. It didn't scale to many pixels and so on. And there's other reasons. But in general, this is an extremely hard problem. Now, similar problems have been solved in the auditory system for a cochlear implant. In fact, these get routinely implanted into patients today and have been for decades. It just turns out that the eye is more complicated, it's more sensitive, and it's just a much more difficult problem. And we're still working on it, and we think that we can do something good here, but we have to understand, at least for the purposes of this course, understand a little bit more about photoreception before we can get into how we would, for example, design a retinal prosthetic. So if we want to build a good silicon photoreceptor, we want to integrate it into our integrated circuits, then let's first learn about how the eye does phototransduction. This might be useful in our pursuit of understanding how to build good artificial phototransducers. So here's a cross-section of a human eye. So you can see the classical things, the cornea. This is part of the lens system of the eye, where light rays enter here and then get focused through this lens system here, and eventually these rays find their way to the back of the eye over here. This is where the retina is. So kind of all along here is the retina. Now, the retina is composed of many cells. We'll talk about them momentarily. The fovea right here is the sharpest area. This is our central vision. This is responsible for reading, writing ECE203 exams, driving, etc. Okay, so when you are using your central vision, this is when light is hitting the center area of the retina called the fovea. Now over here is what we would refer to as the peripheral view. Okay, the light that hits over here is what you can see kind of in your periphery. So if you're looking straight ahead, you can kind of see that there's something going on to the sides. If you wiggle your hands to the sides of your vision, you can see that your hands are wiggling, but you don't get super good resolution of what's going on there until you bring your hands right in front of you as an example. So the retina is composed of millions of cells that act as photoreceptors. Okay, so these are, what are transducing incoming photons into the ionic signatures that travel along the optic nerve to the brain to experience vision. So there's different types of photoreceptors. There's rods and there's cones. Okay, so cones are concentrated in the fovea. They have very high acuity, and they are these are how we sense color. Okay, so there's 3 different cells, different types of cones, and they respond primarily to 3 different types of wavelengths, although as we'll see, it's a transfer function. And this allows us to see in color. Okay, now the cones, they have a fast response time and low sensitivity. So they're primarily for daylight vision. All right, so when you're looking at something right in front of you, typically you need pretty good light in order to experience the colors that you can see. There's about 6 million of these in the retina. Now the rest of the retina is composed of cells called rods. These are mostly concentrated in the periphery. They have fairly low acuity, which means you don't get as good spatial resolution, but they have very good sensitivity. And as a result, this means they're primarily for night vision. Okay, so at night there's not a lot of photons hitting the back of your retina, and when only a few photons hit a cone, they just don't really respond, and so your brain doesn't interpret information that's coming into those cones. But your rods, you can think of them as a high gain amplifier if you like, they do respond. In fact, a rod can detect single photons. This is amazing, actually. Now, because they're sensitive, they're also slow. So they have a slow response time. And there's only one type of rod, and so as a result, we can't distinguish colors in your rods. So this might actually sound familiar to you. If you're driving, for example, at night, typically your vision is worse at night, right? There's less photons hitting your eyes, so that makes sense. In fact, we end up suffering from shot noise more at night because of Poisson distribution of arrival of photons. And we don't activate these cones very much. So when you're driving at night, it's generally harder for you to get really good sense of color, right? It's hard for you to see the greens of the trees and so on in dim moonlight, for example. You can see that there's trees there, but it's hard to see that they're green, right? That's because most of your vision is occurring due to these rods, and they don't perceive color. They perceive brightness. In addition, if you're driving at night, you might find that your response time when you're driving is a little slower than it is during the daytime. And that's actually physiological. It's because your rods have a slower response time. I mean, there's other factors at play here, but this does contribute to it. So you can't see as good in the night. There's more noise, there's more shot noise, and so on. And you can't see color very well. And you have slower response time. So this is why some people really don't like driving at night. Okay, but of course, we can still do it. It's just not as good as in the daytime. So if you take a look at what the actual structure looks like, it looks something like this. So on the right here, you can see a three-dimensional image. You can see the cones and the rods. You can see the rods are much larger, physically larger cells. The cones are smaller cells, and so on. And the other thing that's really interesting is that light hits the retina like this. Okay, but it turns out that the rods and cones are way back here. All right, so this is actually somewhat of a familiar structure here. Think of this over here as the substrate. Here you have your doped silicon regions, and above here you have your metallization. Well, that's basically what's happening in the retina. We have our rods and cones at the back. We have these other cells, the ganglion cells and so on. This is basically the interconnect that is connecting these rods and so on to other areas in the retina and eventually to the optic nerve. So what we can say here is that this is a system that is not backside illuminated. For those of you who are familiar with how digital CMOS cameras work, there was a shift many years ago, I guess now, where previously we would build CMOS imagers just like this. We would have the pixels, the photodiodes on the substrate, but then we'd have to go through some of the metal layers and the interconnect and so on before the light actually hit the photodiodes. Now we typically will use a backside illuminated system where we flip the structure around and we have the light hit directly the photodiodes from the back, and then we can fill up the top with all sorts of interconnect without having to worry if the light can actually reach the photodiodes or not. Okay, and this was a way that engineers were able to improve the low light sensitivity of cameras. In particular in smartphone cameras and so on, these are finally making their way into digital SLRs now. So here's a cartoonish diagram, if you will, of what these rods and cones look like, rods on the left and cones on the right. And these are basically just one, or two different types of large cells. Light will hit these areas here, although of course the light is coming from this direction over here. And in here, and we'll study this a little bit more shortly, will eventually cause some chemical imbalance to happen in the cell. There's going to be some sodium channels that close and therefore cause a chain reaction that will create an action potential that gets sent along the synaptic body, for eventual translation across the optic nerve into the brain. The same thing happens over here. Light hits this area over here, and eventually you get some synaptic communication that happens at the bottom of the cell. Now, of course, we could go through all sorts of detail into how these cells work in much more detail, but what I'd like to focus on is how do we represent color based on the fact that there's one set of rod cells and three set of cone cells. So if you go ahead and plot the responsivity of a particular cell to different wavelengths of light, you'll plot a graph that looks something like this. And I should mention that this center piece here is the rod response. Okay, so one question we have here is, okay, so I take a single cone cell, let's call it the blue cone cell, and it responds most strongly to light in the blue range here, but it also does, respond a little bit to light in the green range over here. There's not a zero response, whereas, in the solidly green range, that we get a very strong response from the green cells, and we get some response over here from the red cells. It's actually kind of more in the yellow area over here. So it's quite interesting. How are we seeing color based on all of these responses? So colors exist in a continuous spectrum, right? There's an infinite number of colors. They exist across this entire spectrum, and yet we only have three different cones that respond to three different colors. So what's going on? How do we see over we'll call it a pseudo-continuous spectrum? The answer, as it turns out, is linear algebra. Okay, so the idea here is, yes, we do have 3 different cells that primarily respond to 3 different colors, though not exclusively to those 3 different colors. So if you get light coming in kind of the green spectrum, you'll get a very low response from the blue, quote unquote, blue cone. You'll get a strong response from the green cone and some mild response from the red cone. The linear combination of these 3 different responses creates a signal that goes to the brain, and the brain interprets this signal as, some specific color. Okay, so you can imagine that across the spectrum, you can have all sorts of different permutations and combinations of vector response to these 3 different cone cells, and this creates the continuum of spectrums that we can, as humans, see. Now, there's an interesting caveat here in that we are all colorblind. And what I mean by that is that there are an infinite number of colors that we call metamers that elicit the exact same response from the 3 different cone cells. Okay, so you get the same response even though they're at different colors. So technically that means we're all colorblind. However, the 3 primaries that we do have in the human body are good enough for most color representation. I guess we don't really know any better because we don't have more cones than the 3 that we have. So I suppose we don't know what we're missing, but I would imagine that most people feel that they can see enough colors to make do. Now, of course, there are what we would call nominally colorblind people who are missing a particular type of cone. And as a result, they can't distinguish between certain types of colors. So this is what we would call someone who is colorblind, but not colorblind in the general sense due to metamers. So there's an easy test for colorblindness. If you can read what's inside these circles here, then chances are you are not colorblind. But if you can't read what's inside these circles, then maybe you are colorblind. I don't know. I'm not an expert, but maybe look into it. So let's take a little bit of a closer look at what's happening inside these photoreceptors. Again, there's a lot of complicated biology going on here, but the idea is something that we can somehow grasp given our previous knowledge. So light will go in and hit this visual pigment that will cause a chain reaction that will eventually cause a sodium channel to gate itself. Okay, and that's really ultimately the key that's happening here. So here's another look. When there's no light coming in, then nothing's happening in the photocell, and we get a nice flux of sodium going across this channel. If we have a nice flux of sodium going across this channel, of course the cell must be in equilibrium, so there's a equivalent flux of something going out, and that will establish some sort of resting Nernst potential. Okay, but as soon as light comes in and hits, it causes this chain reaction which clamps down this sodium channel and closes it. All right, and what that does is it'll certainly change the ionic concentration of sodium inside the cell, which will cause the Nernst potential across the cellular membrane to change, perhaps in a way that will cause some, it turns out that in retinal cells, it's a hyperpolarization process as opposed to a depolarization process, which is what typically happens in a neuron. So as we know from our discussions on cellular ionics, if we know the relative concentrations of ions inside the cell and outside the cell, then we can set up our Nernst equations and if we can figure out the conductance of the ion channels, we can go ahead and figure out what the overall membrane potential is. So it turns out that in resting cases, the Nernst potential for potassium is minus 70 millivolts, and for sodium it's plus 26 millivolts for this type of cell. And the normal resting potential is minus 40 millivolts. So you could, infer the relative conductance of the potassium versus sodium channels through some inference here. So when there's incident light that hits the cell, then the resistance of the sodium channel will increase. okay, basically because the sodium channel is clamping itself off. As a result, this actually drops the membrane potential. So normally in dark, we're sitting at minus 40 millivolts. And when light hits the cell, we actually drop closer to the minus 70 millivolts for potassium, because potassium, its resistance is nominally not changing much during this time. So as a result, we basically drop all the way down to minus 70 millivolts. This is why we call this a hyperpolarization event, as opposed to a depolarization event, where the potential goes positive instead of getting more negative in this hyperpolarization case. So one thing the human body does very well is we have this ability to see in very low light conditions, and yet also the ability to see in very bright conditions, usually not back to back. So we have this adaptation that happens physiologically between all cone daytime vision and all rod nighttime vision. So, you've probably experienced this many times. You're in a dark lecture hall or something like this, and you go out and you go out into the bright sunlight right after class, and you're like, wow, the sun's really bright, I can hardly see, and you have to squint for a little while and so on. And eventually, maybe after a short time, it'll get better, and then after 20-25 minutes, you'll be fully back to normal. And then if you go back into this dark room, you're not going to be able to see anything. So this is a physiologic process. There's a number of factors that are happening here. The diameter of your pupils is certainly one. The wider your pupil, the more light is entering into your eye and hitting the back of your retina. You can think of the diameter of your pupil like the aperture in a lens in a camera, for those of you who are into photography. And then there's other kind of more active gain control systems at play here. So, in some of the previous slides I showed, there's this chain reaction that's going on here, and this biochemical cascade is kind of acting as an amplifier, a signal amplifier. It's a little bit more complicated than that, but basically that's what's happening. And so when it's dark for a long time, then there'll be an adjustment of the gain of these circuits. There's a little bit of a feedback loop that's going on here. Now, interestingly, this dark and light adaptation is possibly, although this has not been historically verified, a reason why pirates wear eye patches. In fact, there was a Mythbusters episode about this, and the theory goes is that if a pirate is, on board on deck, and they need to quickly go under deck to, I don't know, get a bottle of rum or fight somebody or something, it's really dark under there compared to the brightness above. And so the idea here is if you have a patch over one eye that's not letting any light, then that eye is adapted to the dark, the other eye is adapted to the light. And so when you go down below, all you have to do is take that patch and shift it over to the other eye and open the eye that was nominally covered by the patch, and it's already adapted to the dark, so you can see much more easily. Okay, so this is the hypothesis. Again, it's not historically confirmed or anything like this of why pirates have tend to do this, at least in media representations. But in the Mythbusters episode, they did test this out, and they determined that it was plausible that this was a reason why pirates would do it. If you ever want to experiment with this, let's say you have to get up in the middle of the night to go to the bathroom or answer an email or something like this, then try keeping one eye closed while you do it. Turn on the lights, and so on and so forth. And then when you turn the lights off, switch the eyes that are open and see if you can see a difference in your ability to see in the darkness. And some of you may be able to see a difference. I've tried it myself. It's kind of fun to try this. So the human body does do this kind of adaptation quite nicely. So one interesting thing that the body does is it does adapt to these dark and light conditions, but at the same time, we're still able to see things relatively clearly in either condition. So for example, you can read a book in a fairly dim, although not totally dark, but a fairly dim room. You can read a book just fine. There's a finite contrast ratio between the black of the text and the white of the page in your book. And then you can take that same book and go outside into direct sunlight, and after your eyes have adapted for a few minutes, you can still read that book. Okay. Or perhaps a long time ago, you could see a tiger in the jungle whether it was light out or dark out, or although of course you could probably see it a little bit better if it was light out for reasons we discussed earlier. So what this means is that the eye is generally looking for localized contrast. And that's really important because we want to be able to see that tiger in the jungle regardless of the absolute light level. If we only responded to absolute light intensities, we would need an incredibly large dynamic range system to experience these different light intensities, and we would have a hard time finding the difference between a tiger in a very bright jungle versus a tiger in a very dark jungle. Relatively speaking, these are very close in amplitude, for example. So what the body does is this kind of slower adaptation. So what we're showing on this slide is the relationship between the input and output of cone photoreceptors. So what we're seeing with these curves here is the instantaneous response. Okay, so what I mean by that is if we're in kind of some room with some nominal amount of ambient lighting, we'll get this kind of instantaneous response when you flash a light or show something with bright contrast ratio or something like this. In other words, we get a large amount of gain locally over the small level of range, and at the peak of this gain curve, we saturate actually, right? And that makes sense because when you instantly go outside from a dark room and it's bright outside, you can hardly see anything. Your cones are saturating. Okay, but these curves shift with a slow, steady state response. Okay, so this middle curve is what we call the steady state, or the for lack of a better word, the DC response. So what this means is if you happen to be in a very bright outdoor scenario, so the average log intensity is over here, then you're going to get roughly the same amount of gain in your system over here as you would in a very dark room. Okay, that means you can read that book, you can see that tiger, and so on. It doesn't matter what the absolute level of light intensity is. Or in other words, the gain is relative to the absolute response. So the gain is proportional to the change in light intensity divided by the actual light intensity. This is something that the human body does very well, and it's something that perhaps we ought to learn about in the pursuit of building a good artificial photoreceptor. So to demonstrate this adaptation, I'm going to get you guys to look at this picture. This is called the Spanish Castro illusion. So stare at the black dot and don't move your eyes. And I promise there's nothing scary that's going to pop out or anything like this. Stare at the black dot and see what happens. Okay, the image changed, and you should have seen something curious happen there. You should have seen that some of the color actually looked normal. You're looking at this picture, and we'll repeat the animation again here. The color actually kind of looked normal when the image flipped, and then it turned to black and white. So what happened? Let's try this again. Very interesting, isn't that? Okay, so what's happening here is a negative after image. It's caused when the eye's photoreceptor, primarily the cones, adapt from overstimulation and lose sensitivity. So normally the eye deals with this problem by rapidly moving very small amounts, and this motion is kind of filtered out, so it's not noticeable. But if the color image is large enough that the small movements are not enough to change the color under one area of the retina, the cones will eventually tire or adapt and stop responding. So in other words, the cones are so used to getting really blue intense light in the middle where this castle is, that the relative gain of the blue cones basically just goes down, okay? And as a result, when you actually get blue light, or when you actually get blue light, then your eye or your brain perceives it as being very blue, because the gain of the blue cells sorry, I said that wrong, is so low, okay, because it's being overstimulated. So when the image turns to black and white, and it truly is black and white, black and white has, you know, a full spectrum of colors that hit your eye, some of which is blue, and so as a result, you see a blue sky in the area where your blue cells are in a very high gain state. So in the sky where it's yellow, your blue cells aren't being activated at all or hardly at all in that area, and so as a result, your eyes are adapting the blue cones to be in a very high gain state. And so when we get this black and white, or this gray image, I guess, then that really activates the blue cones and turns them on into a high gain setting. Now, interestingly, if you look at the illusion, you're seeing color and then you just quickly flick your eyes to the left or to the right or some other direction and then look back, then almost instantly the image goes back to black and white because the eyes will adapt to this new situation, and then the gains will all kind of render themselves out. Okay, so this is called the Spanish Castle illusion, and it's a very nice description of, or demo, I guess, of how our eyes are doing this real-time adaptation. The other thing I'd like to note about the the optimization of our biological system is that the response time is actually fairly compressed, I would say. So what we're showing here is the response time on the y-axis versus gain in arbitrary units on the x-axis. So when gain is low, we tend to be in a bright light condition, and when gain is higher, we tend to be in a low light condition. And what we say here is that the response time, at least dynamically, is fairly compressed. Okay, so in this case, it goes as the fourth root of intensity. So this means that over a factor of 200 in background intensity, the response latency to a flash of light varies by only about a factor of 4. So this is also actually a nice feature. It means that if we're looking at a moving image and we're trying to spot, I don't know, a black panther or something in the jungle, because we want to obviously not get eaten by the panther, then our eyes will be able to see this dark, motion moving relatively well in response to an overall bright scene. Okay, so this is also kind of another nice biological optimization that happens inside our bodies. So now that we have a little bit better understanding of how biology does it, let's take a look at how we can do this electronically in silicon. So in silicon, we tend to build photoreceptors using what we call photodiodes. The most basic photodiode is just a pn junction. And if an incoming photon hits a pn junction, it creates an electron-hole pair, which causes current to flow in this diode. It'll actually photobias the diode. What we typically do in photosensing applications is we actually want to reverse bias the diode because this puts it in a more favorable operating condition that improves the speed and actually makes the biasing of the circuit quite a bit more simple. Okay, so normally when we're designing circuits to do photodiode current amplification, we will model our diode as a current source with some, parasitic capacitance associated with it. So normally what we do when we want to amplify the current coming out of a diode is we will use what we call a transimpedance amplifier. A transimpedance amplifier is nothing more than an amplifier that takes in an input current and outputs an output voltage. So in this particular case, we can analyze the DC response. So due to, the DC response, I guess, with an AC small signal model, so in other words, ignoring the capacitance. So at AC small signal, this terminal here is a virtual ground, and no current can flow into the op amp over here, so all of this current must therefore flow across this resistor RF. So we can say that the output voltage, V out, is equal to I in times RF plus Vref. This is the DC response of this particular amplifier. Now, of course, we're not typically only interested in amplifying DC signals, so let's go ahead and look at the AC response next. So in order to figure out this AC response, this is not a super complicated circuit. We could do this easily analytically, but perhaps this is a good opportunity for us to exercise our block diagram creation skills. So we can go ahead and construct a block diagram, minus I in. I know that there's going to be a current summation node here, so I'll put that there. So this is a current. The current must be multiplied by the driving point impedance at this node here. That's just RF in parallel with C in. So if we represent that as an impedance, that's RF over 1 plus SCN times RF. Okay, so that's the voltage now at the front of the amplifier. The amplifier has a gain of minus A. I'm not going to bother with the feed forward path because we know that it's going to be much less than this gain through this op amp. But we will obviously put in the feedback path, which is 1 over RF. And over here as follows, and this is, well, as written, positive feedback, but of course we know that the A will end up being negative. So I in, let's just redraw this to make it a little easier to understand. RF over 1 plus SC in times RF. In this case times plus A, V out, 1 over RF in feedback. And now we're in negative feedback here. Okay, so we can go ahead and write down the transfer function, V out over I in is equal to A times RF over 1 plus SCN RF plus A times RF over RF, which is equal to A RF over 1 plus A. I'm just rearranging this in a way that will make sense, hopefully shortly, plus 1 plus S times Cn RF divided by 1 plus A. So one question you might ask yourself is, why do we even need the amplifier? Okay, the amplifier doesn't seem to be providing any function here, right? The current could just easily go over that resistor without needing the amplifier. And that's true. You don't technically need an amplifier there, an op amp. You could just run that current over the resistor. The amplifier does provide two purposes. One is that it stabilizes this, I guess we'll call this the Vx node here, to a suitable reference voltage, Vref, in order to reverse bias that diode. But also, if you note here, if we didn't have the amplifier, if the amplifier's gain was not there, then you would see we would get basically a first-order low-pass filter set by the RFCin time constant. But in this case, we are expanding the bandwidth. That pole is now at a factor of 1 plus A larger, or higher in frequency. So by adding this amplifier, not only are we allowing a good bias condition for our diode, we're allowing the circuit to have a much larger ultimate bandwidth. So now I want to modify things a little bit. I'm going to take the output of this amplifier, and instead of passing it through a resistor, I'm going to pass it through a sub-threshold MOSFET. And the reason I want to do this is I'm trying to learn from biology. I want to make the gain logarithmic instead of linear, so that we get a contrast instead of a nominally linear relationship. So the only place that current can flow through this circuit, at least at DC, is this way. Okay, so the DC current of the MOSFET is going to be dictated by the photodiode current. Now the photodiode current is going to be pretty small, so as a result we can pretty much safely say that this transistor is going to be in subthreshold. So its subthreshold current is given by IDS is equal to I off times e to the VGS over n phi t, and ignore all the other body effect and so on. I'm going to assume we're saturated as well. So we can solve for VGS. This is equal to n phi t times the natural log of IDS over I off, right? So that gives us VGS. That's this voltage here, VGS. So we can actually go ahead and now say that, well, actually this is equal to Vout minus Vref, right? If that reference voltage is indeed, or if this gain of the op amp is very high and that's virtual ground. So we can say then that Vout is equal to Vref plus n phi t times the natural log of I in divided by I off. This is the DC response. Okay. So let's go ahead now and figure out the AC response. Now to do this, let's first set GF to be equal to IDS over n phi t, which is, in other words, equal to I in, DC value of I in over n phi t. Okay, so we have I in coming into this current summing node. We multiply by the driving point impedance at this Vx node here. Now, if you recall, the impedance looking up into the source of an NMOS transistor is just 1 over GM. In this case, GF due to this subthreshold circuit. So we can say that the driving point impedance here is 1 over SCN plus GF. Now you could derive this from the small signal model if you liked. This is just a quick way to get this answer. So this goes to Vout, and then to feed back, well, the response between a gate voltage and the response feeding back into a current is also just the transconductance. So it looks something like this. Okay, so that's our feedback loop. So again, what we can do is we can take our transfer function Vout over In. This is equal to A over SCN plus GF plus A times GF, which is equal to 1 over GF times A over 1 plus A plus SCN over GF, which is equal to 1 over GF times A over 1 plus A divided by 1 plus SCN over GF divided by 1 plus A. Okay, so similar kind of thing here. We're seeing that the amplifier does provide this bandwidth expansion. And now we can solve for Vout. Vout is equal to n phi t times little I in over DC I in times A over 1 plus A divided by 1 plus SCN divided by GF times 1 plus A. Okay, so this is exactly, in fact, exactly what we were hoping for. So in other words, what we're saying is that the output voltage in this case, all I've done is replaced GF with the definition I showed above there, is that the output voltage is now proportional to the AC input signal and inversely proportional to the DC of the input signal. In other words, it's equal to n phi t times delta In, or the change in the input current, divided by the absolute input current times, blah, blah, blah. Okay, so if you recall, this is exactly like what the I is doing. It's sensitive to fractional changes in the input current, or in other words, it's sensitive to contrast. So that's exactly what's shown on this slide here. We're sensitive to fractional changes, delta In over In, just like the I. We still get our bandwidth expansion of 1 plus A. Our minimum detectable contrast is now input current intensity invariant, since the bandwidth is proportional to GF, which scales with In. So this whole circuit, it's actually very beautiful. It's kind of like having built-in automatic gain control. It's kind of like this feedback factor, which was previously RF, but now is this transistor MF, changes dynamically such that In times RF remains constant. Okay, so it's like we have this dynamically varying RF that is adapting itself just in the right way, such that we get this nice logarithmic response, just like how the eye works. So now that we understand a little bit more at kind of the block diagram level here, how are we actually going to go ahead and build a circuit that does this? Well, a photodiode, again, is just normally just a PN junction, reverse biased. When photons hit this PN junction, it creates a current that we can go ahead and measure. But we don't want to just, if we just have this PN junction, then, we don't want the voltage at the P side to go below ground. And in fact, in this particular case, it's literally just the substrate of the chip, so it's tied to ground. And we don't want the N plus region to go below that value. Otherwise, we have other weird diode issues that can show up here. So what we often do is we actually build this photodiode into a PN junction as part of a transistor, which is shown on the right here. So the drain of the transistor is connected to VDD. The gate is biased to an appropriate value such that Vout, which is controlling now the bias or the reverse bias of the diode, is set such that N region is biased to an appropriate value here, so that it doesn't go below ground. And in this particular case, we can ensure that the transistor is biased in subthreshold because the current flowing through the transistor is just dictated by the photocurrent, and it actually doesn't really matter what the gate voltage is. Vout will adjust appropriately to make sure that the transistor is still operating in the subthreshold regime. So we don't want to just build this circuit because this photodiode will have some parasitic capacitance. It has very low current, typically, depending on the size of the photodiode and the light intensity. But if we're talking about 100 femtofarad of capacitance and 4 femtoamps of current, which are realistic numbers depending on the process and the light intensity, then we're talking literally about a 1 Hertz time constant, which is very slow, particularly if you want to build a camera kind of system. In addition, we might have some DC offsets, right? If we have threshold voltage variation through that transistor, the output voltage will be affected fairly strongly. So the solution is this feedback circuit. Okay, so the circuit that we just looked at is right here. We're going to call this the source follower, which includes the photodiode. The output of the source follower, we want to put through a gain circuit. We want to have some gain in our feedback loop. And then we want to have some sort of feedback circuit that feeds the output of this gain block back to the source follower in order to provide some feedback control of the circuit. So let's go ahead and break this circuit down. So part A is the overall circuit. Part B, we're going to call this the log source follower. This is basically what we just derived in that previous circuit that we talked about. And this gain stage in part C here, this is just a cascode amplifier. Its gain is equal to minus GM1 times the load, which in this case is RO4 in parallel with 1 over SCO. We're going to assume that RO4 dominates here because it's not cascoded, whereas M1 and M2 are cascoded, and so the impedance looking down into M2 is going to be much larger than the impedance looking up into M1. And then this circuit here will ignore for the moment this mysterious RA block here, but if we ignore for the moment, we just have this capacitive divider, which at AC is going to provide some sort of voltage divider. Okay. So now let's go ahead and derive the feedback diagram for that circuit. So we have minus I in. It's going to go into some current summing node here. And then the driving point impedance, just like in that other example, is 1 over GS3 plus SC in. GS, as you'll recall, is GM plus GMB for that transistor. Our forward gain path is minus GM1 RO4 divided by 1 plus S RO4 times CO. And this creates our output voltage. Our feedback is going through this at AC, through this capacitive divider, C1 plus C2. That generates the, this is still a voltage actually, and then GS3 generates the current, which we then add over here. So what I'm going to do is I'm going to take this GS and I'm going to push it over here. Okay, if I push it over there, I do need to modify the input. It's now I in over GS3. I'm also going to take care of that negative sign at the same time. And then this becomes 1 over 1 plus S C in divided by GS3. I'll just lump it into that equation here. I'm going to call this A over 1 plus S times A times CO over GM1, where A is just GM1 RO4. This is V out. And then I'm going to feed back through C1 over C1 plus C2. And technically now this is a voltage signal that we're feeding back here. Okay, so this is the block diagram of our system now. So we can go ahead and write some simplifying expressions. So I in over GS3 is equal to I in, this is the AC component of I in, over IL over N phi t. This is the current flowing through that transistor, which is equal to delta IL divided by IL times N phi t. So that's just writing out the expression for the input signal into this circuit, which is I in over GS3. So if the loop gain is large, we can then say that V out divided by delta IL over IL times N phi t is equal to, well, it's just the reciprocal of the feedback factor. It's equal to C1 plus C2 divided by C1, assuming the loop gain is large. So what we can then say is that V out is equal to N phi t times C1 plus C2 divided by C1 times delta IL over IL. Okay, so with this circuit, we are maintaining this desired contrast ratio, or contrast, I should say, response, like the eye. And we're doing so in a way that is relatively simple. We don't even need a full op-amp to do this. We just needed basically a common source amplifier and a feedback factor. Okay. Now, you might be asking, well, what was that RA thing? What was that RA circuit? It turns out it's a MOS bipolar pseudoresistor. They called it an adaptive resistor. It's basically just a resistor that has a very large impedance. It's exactly the MOS bipolar pseudoresistor that we studied in the instrumentation amplifiers lecture. So one interesting thing is that at DC, capacitors C1 and C2 are ignored, right? They're super high impedance. Now, we can't have any current flowing into the gate of transistor M3. So despite RA being this incredibly large teraohm kind of style resistor, it's basically a short circuit at DC. Very interesting how that works, right? There's no current that can flow through the gate of the transistor, assuming we're using a process that doesn't have appreciable gate leakage. So as a result, the current that flows through RA is basically nothing, right? So as a result, whatever voltage is seen on the right of RA is basically just going to find its way to the left of RA. So even though RA is a huge resistance, it's basically acting as a short circuit at DC. So for DC, this means that we basically have the same expression for the output voltage as we had for AC, but without that capacitive divider ratio. So we basically just have this expression here. Okay. So depending on the size of C1 versus C2, this basically means that we get a larger AC gain than we would get for DC gain. What this means is we now have an adaptive amplifier, just like the eye. We have something that has larger AC gain than it has DC gain. And so as a result, here's some measurements from Carver-Mead's group at Caltech describing this. We can see that the steady state response increases slowly with the log of the intensity, and yet the transient response has fairly large gain instantaneously. That's exactly how the eye is working, and that's exactly what we've been able, or what they were able to build in this particular circuit. So as I said, that adaptive resistor, this MOS bipolar pseudoresistor, is usually a very large resistance. And under very bright light, the bipolar resistor essentially turns on, which actually significantly reduces the resistance of RA. Okay. So under low light conditions, the response time will be 2 seconds, whereas under bright light conditions, the response might be half a second, something like this. So you can see here how this adaptive resistor is another piece of the puzzle here that is allowing us to automatically adjust the performance of this photoreceptor in a way that, largely mimics the performance of the eye. So I thought this was a very clever design and something that I thought was worthwhile studying. It also got us to break out our block diagram synthesis techniques to analyze it and so on and so forth. So that'll be, I think, it for today's lecture.